Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
Today I will continue and prove Jacobian criterion, assuming the two lemmas we have proved, and I will recall those two lemmas when we actually need it. So, let me just recall what we want to prove and what are the ingredients. So, today the goal is, and then we will state precisely, we want to compute or calculate the singular locus of an affine algebra A, which is kx1 to xn modulo some ideal, modulo the ideal, and the generated, finitely generated, therefore it is generated by some m polynomials, and this ideal we will write it here. And what does one mean by singular locus? That means all those prime ideals in this affine algebra, so that the localizations there are regular localizations. So the prime ideals will look like P by A, where A is an ideal in the polynomial ring, and this P is a prime ideal which contains A. So this P is actually prime ideal in the polynomial ring, and we are looking at every prime ideal in A looks like this. So that is the notation, and we want to know when exactly the local ring A localized at this P by this is regular local, is regular. And such a criterion, you see, in general it is not easy for arbitrary commutative ring to decide what are exactly the prime ideals where it is regular, but for a affine case it is easier in terms of the equations. So that is what we want to know, and what this is our goal. Okay, so what are the ingredients in the proof that we will need? So the answer will involves first of all, it involves irreducible components of the spectrum which contain this given prime ideal P by A. So in this is in purely algebraic language. So this means minimal primes of the ring A. That means minimal primes A contained in Q, contained in P, where these are in the spectrum of kx1 to xn. So in kx1 to xn, this P may not be minimal over A. So we look at the minimal primes of A, which are minimal over this. These correspond to the irreducible components. And what else? So this is one, and the matrices, the rank. So the matrices we got it from the defining equations of A. So the rank of the matrices, and how do the matrices arise? That is by differentiating. So I will just write rank of a matrix like this. Some polynomial Gij, the entries are in Gij, and their entries are in, actually this is a matrix of some order. I will just write here M and K. Entries are in the polynomial ring mod a prime ideal, and that you can think, because this is an integral domain, you could also think that these matrices are contained in a matrices with entries in the quotient field. So this is subset of M, M, K, then the quotient field of this. So therefore the usual linear algebra should help us to compute this rank. That's what last time also in the two lemmas this was seen. Okay, so to be more precise now, let us state what we want to prove. So the theorem we want to prove is this is called Jacobian criterion because it involves the Jacobian matrix. Okay, so as usual earlier notation, F1 to Fm are the generators for the ideal given ideal A, and also we have given a prime ideal P, which is everything is happening in the polynomial ring in n variables over a field K. K is a field, okay, and Q is a minimal prime. In between this Q, this is a minimal prime over A. That is the situation. Okay, so and what are we denoting? I want to denote now. If I take this matrix D Fi dxj, this differentiate these polynomials with respect to the variable xj's and read them mod p. So this is now a matrix M cross n matrix. M are the rows and J's are the columns. Sometimes it might happen that I would have interchange rows and columns. So that you have to watch out. If you have trouble in one way, try the other way. But mostly it should be correct. This matrix I want to denote because every time it's too much to write like that. So J for Jacobian, F1 to Fm, and semicolon P. This is called the Jacobian matrix of these equations at P. So Jacobian matrix of F1 to Fm at P. So this is a matrix over the ring Kx1, x2, xn mod P, but that is an integral domain. Therefore, you could also think it's a matrix over the entries in its quotient field. Okay. So the first assertion is A. The rank of this matrix has a bound. So rank of J F1 to Fm colon P, this cannot be more than height of Q. So, as I said earlier, it involves the rank and also it involves the irreducible components. There, this is irreducible component is coming from this Q. Okay, and now this inequality you could also write in terms of rank. So, the nullity. Actually, I do not like to use the word nullity for many reasons, but that is quite popular for engineers. So, this if you use nullity, then the inequality will get reverse. So, nullity of this will be bigger equal to dimension of every irreducible component of spec A, which contains this point P by A. You see, remember, this Q is not only one, there may be many Qs, and we are making this statement. So, that means if this is less than equal to every minimal prime side, and when you take the reverse inequality, it will become every. Okay, that is the statement A. Second, B, then talk about when do equality hold here. Equality if equality holds, in A, then it is regular. Then A localized at P by A is regular local when it's a local already, regular local. So, that is when equality holds. Now, this part C statement will be when the converse of this B holds. That means when exactly the equality holds. So, C part says if actually one wanted to write here if and only if. One would like to have equality holds if and only if the ring is regular local, but that does not always happen. It depends on the base field. So, whether the base field is separable or not. So, base field is perfect or not. So, if the quotient field base field is perfect or not. If the quotient field of this ring kx1 to xn mod P is separable over K, then the converse holds. Then the converse in B holds. So, this will particularly happen in two cases. When the base field is perfect. Characteristic 0 fields are always perfect, and characteristic P case. So, I will just recall what is perfect. So, when this will happen in these two cases, K perfect. Remember, this field is not algebraic over K in general. So, separability should mean that there exists a separating transcendence basis. That means the algebraic part of the after you attach a transcendence basis, the algebraic part is separable extension, and that means algebraic extension is called separable if every element has the minimal polynomial does not have repeated roots. Okay, perfect means K to, you have a natural map from K to K, namely any A going to A power P, where P now is not a characteristic, but it is almost like a characteristic. So, P is called a characteristic exponents, characteristic exponent, that is when that is P, it is 1 if characteristic of K is 0, and it is P when characteristic of K is P positive. So when this map is it's clearly a ring homomorphism because of the definition of the characteristic exponent, and when this map is surjective, then it is called perfect. That is the definition actually, surjective. That simply means that every element in K has a pth root, where P is the characteristic exponent. Okay, so for example, finite fields are, because in the case of finite fields, this map is always injective and therefore surjective. So P general principle. So, okay, or it can also happen without base being built. The equality in A, inequality in so this equality can also happen without a K being perfect. For example, it will happen in the case, this is about the P now, when P is, if P is actually a closed point, a closed rational point. So that is P is M suffix A, which is generated by x1 minus a1 xn minus an, where a1 a is a1 to an. This is actually in k power n. So these are very special maximal ideals. These are the maximal ideals where the residue fields are k itself. It's not changing. So the residue fields are not changing. And why in this case? Because let us write. This is very important. I want to calculate this. So in this case, I want to write down the Jacobian matrix. What it means, right? So the Jacobian matrix in this case is what? So we have to differentiate the generators and read them mod P. Now I will write MA. But this is precisely what? This is precisely you are putting xi equal to ai. So that means this is precisely dfi by dxj's evaluated at that a. So this is what exactly you learn in analysis. When you expand Taylor's this, that, you use such an expansion because you need partial derivative and evaluate at a point. There it was there was no prime ideal, there only the points were there. So therefore in this case, the Jacobian matrix f1 to fm at P, this is the Jacobian matrix of f1 to fm at that point A. This is more familiar object. So this is also called functional matrix at A. In analysis, people they call it also functional matrix at A. Okay, so and therefore also one more comment that because in this case the residue field will not change. This field is K itself. So therefore there is no question of separability. It's separable always. Okay, so also this matrix, in this case this matrix is also denoted by, in analysis it is denoted by a differential of f, the map f at A, where f you think of it's f1 to fm, and think of this is a map from km to kn. This usually do it in real numbers, so or complex numbers. Think of this as km to kn to km actually, and then you differentiate and take the total differential and evaluate at the point. The total differential at A is precisely given by this matrix. Okay, so that was it. Yes. Yeah, equality in A holds, then the ring is regular. No, no, that the height comes only the equality here. Also, that will, you see, it will also be clear because you remember, it will come in the proof that this P will not contain more than one minimal prime. Then the question will not come, right? That will happen because if you remember an example, last time I gave an example, if a primordial P lies on two irreducible components, then it cannot be non-singular. It has to be singular, right? So because of that, this will not happen. Okay, so now let us, okay, so therefore in that notation, I have not completed the sentence here. If you take the differential of this map at A, this map, see this map is the kernel of this map, it is a linear map and the kernel of this map is called the tangent space at A. So, the point is singular if the dimension of this is more than the lower bound. You remember I said about, we are saying about rank is less equal to height, but that inequality when you use instead of rank nullity, then the equality will get reversed. And just now I said the kernel is the dimension of the kernel is the nullity. So this kernel is a tangent space. So the tangent space will have more dimension than the lower bound. Okay, so that's it. Now let us prove. So proof of Jacobian criterion, and then we will work out some examples, concrete examples. Okay. So A and P is here, and first I want to choose, the statements A and A, B, C are about the given minimal prime which is contained in A and P. But now I choose Q naught here. So Q naught is minimal among all the primes which are in between here. So this Q naught is the minimal among all primes in between. Actually minimal among all minimal primes in between. And you look at all minimal primes of A. So among them you choose the minimal one. So that means it exactly gives the irreducible component. So the otherwise, you see there are embedded primes. So I am taking the Q naught is the minimal one. Then, but we want to prove about Q. So Q naught will be contained in Q. And now if I prove, see we wanted to prove the inequality for Q, but if I want to reduce to the case for proving to Q naught. So suppose I have proved for Q naught, then I want to say that I can deduce for Q. So assume that we have proved theorem for Q naught. Okay. Then I want to claim that I want to prove it for Q. So for example, so let us look at A. See what do we want to prove? I want to see this rank has nothing to do with Q. So this rank is same. So I want to prove that this is less equal to height q, but if I have taken smaller one, that height is already more. So therefore that is trivially holds, right. So that implies inequality in A for q as well. Also note if q naught is properly contained in q, if this, then what it means that, see, this q is minimal prime, this is also minimal prime, that means this is the embedded one. So that means then AP cannot be regular, because we have seen that these are the two primes and P by A, this is passing through both of them. So therefore that ring cannot be regular. This is what we have seen in the example. So therefore in this case A localized at P by A is not regular. Okay. So what about B? Now B is about if equality holds. So if this is not regular, therefore by B for Q naught, this it's not regular, so inequality cannot hold. So by B for Q naught, inequality in A is strict for Q naught, and once it is strict for Q naught, it will be strict for, and hence for Q. And the converse of B, so finally converse of B is trivially true, since A localized at P mod A is not regular. So all these comments just say that to prove the theorem, I will assume the given Q is minimal among the associated primes of A. Okay, so now therefore we concentrate on the case Q naught equal to Q. So assume Q naught is Q. This is really simple. I might have goofed it a little bit, but when you think about it, just say that if Q naught is smaller than Q naught is strictly smaller than Q, then things are easier. Okay, now what do you want to prove? In this case, we are looking at the ring K x1 x2 xn mod the ideal, and then we are localizing at P, and we are debating whether this ring, which is a local ring, whether is it regular or not, or when is it regular. So this is the maximal ideal here is the P. So the maximal ideal is, strictly speaking, the maximal ideal is P mod A and then localize at P. This is the maximal ideal. So this I am going to denote by M. So we are interested in when Rm is a regular local ring. Okay. Okay. So this is nothing. So, and what is the residue field? Residue field is R by M, which is L, which is you take k x1 x2 xn mod P and then the quotient field of this, that is the residue field. Okay, so therefore, what we know always, the dimension of M by M square as a vector space over L, this dimension is, this is the embedding dimension of R. This is always bigger or equal to the dimension of R. And we are debating when will the equality be. Okay. So, equality here if and only R is regular. But what is the dimension? That we know. This is the dimension is height of P minus height of Q. This is the dimension. You remember that, so I want to recall here. Remember that, suppose I have said this for aside, suppose I have an affine algebra A, affine K algebra, and suppose I have a chain of prime ideals. Of length n, and assume that this is the maximal chain. Maximal means you cannot insert any more prime ideals in between, so that so it's a maximal chain of primes in A, of primes in A, then this n must be equal to the cool dimension of A by P naught. This we would have deduced from Noether's normalization lemma long back, right. So, if you use this, then you also get this equality here. Okay, so that is the dimension. Now, therefore, we are debating when will the equality be here. That means when will this be equal to this. So, we want to analyze now when exactly vector space dimension of M by M square is equal to height of P minus height of Q. This is what we are looking for.